understand that we're on a tight schedule today. And, I've got the lunch slot, so to speak, but okay. So I'll try to stick to the time so that you can have lunch and then enjoy the afternoon. So this is the third session. So last time we discussed a few aspects of the theoretical tools in order to try to make some order inside the multi-scale problem that is flavor physics in general. We introduced several tools related to the notion of separating short and long distances, this weak Hamiltonian, and then going down to very low scales where you have to take into account non-perturbative physics coming from the strong sector. You have to parameterize your ignorance in terms of hadronic quantities, just using the Lorentz invariance and the very basic properties of your quantum theory to know at least a bit about the value of these hadronic parameters. And then we stopped just at the moment where we were discussing a few of the tools that are actually used to extract numbers from for those various unknown quantities. Obviously, all this being with the idea that we want to compare predictions of the standard model or any kind of new physics scenario with experimental data. And on the way, we realized that since QCD is involved, there is only a limited set of processes that we can address with some precision, and precision is a key element in the discussion, because in the end you want to have sensitivity, and you have sensitivity to a very large range of scales, and so you need to have accurate predictions from the low energy scales if you want to be able to extract elements related to what's going on at the high energy scale. So now I'm going to move to, as I said at the beginning, to two different topics where we use all this framework and knowledge in order to check the standard model and or find inconsistencies hinting at new physics. And so, as I said, there are two places where we're going to discuss. So the second one, which is going to be probably at some point during the next session, will be related to the current anomalies in B flavor, in the B sector. But this time I will start with questions related to the CK matrix. So determination and CP violation. Obviously, the CK matrix does not contain only the question of CP violation, but it is one of the key ingredients in the determination of the CK matrix. And so I will spend a bit of time giving a few more elements concerning the structure of the CK matrix in the standard. Obviously, that's in the standard model. So I remind you that the point where we had the CK matrix entering the game was when we looked at the coupling of the W plus and W minus with the quarks, and when we try to express everything in terms of actual mass eigenstates, we realized that there was a crosstalk between generations that was embedded in the CK matrix. So I remind you that it's when we're discussing the structure. So you've got the Yukawa giving you mass matrices, quote unquote, that you have to diagonalize, actually perform a singular value decomposition. When you do that, you have to rotate the U left and the D left quarks by different, in principle, unitary matrices that are fixed by you, by the Yukawas that you had at the beginning. And then you realize that when you do the rotation on both U and D, in general, unless there is some kind of alignment between the various Yukawas you have, those two matrices don't cancel, but they go into the CK matrix that is different from unity. And in principle, in general, that could be anything. And last time we also discussed the fact that this unitary matrix has 4 parameters, actual physical parameters. You've got many more, but actually we discussed the fact that we have redundancy, and in the end, when you compute, you take into account all the various constraints that you have, both at the mathematical level and the physical level. You've got 3 moduli in one phase, and actually, because we discussed that during the first lecture, the fact that you have a phase means that the CK matrix is not a real matrix in any kind of convention you may use, and then that means that you have CP violation through this single phase, making the standard model extremely predictive concerning CP violation. So if you try to parameterize this, so you've got a different parameterization that you can imagine. So one which is more related to the idea that somehow you're trying to have an orthogonal matrix with some kind of phase going around. So you can try something which is a bit Euler-like parameterization. That so you've got 3 angles that will be a way of encoding the moduli, and then a phase. And then you can write, so if you introduce some kind of notation for the cosine and the sine, sorry, Cij and Sij, for the various angles that you're introducing, you can say, you can show that one possibility for the generic parameterization of the CK matrix would be something of this kind. So it's slightly tedious. I'm not going to, it's essentially so that you can see exactly what it is. So this way of writing things is completely general. In principle, you could imagine any kind of structure for the CK matrix that would have this kind of obey this kind of structure. So free, C2 free, C1 free, and I should have said before that, okay, this is VUD, VUS, VUB, VCD, VCS, VCB, VGD, VGS, VGB. Okay, now the point is that it turns out that even though in principle you could imagine any kind of structure obeying this these equations, it turns out that V is extremely hierarchical, meaning that it's essentially one identity plus small corrections. And actually, that's why it took us actually a bit of time to understand what was the situation, because when we started discussing the first 2 generations, for instance, it looked like this could be analyzed in terms of without taking into account this kind of mixing, and so that you could just say that V was just the identity, and it took a bit of time to introduce the Cabibbo angle and to understand that there was some mixing at the level of the interaction when you were living in the situation when with mass eigenstates. And so that's why this actual very strong hierarchy of the CK matrix was at the same time very useful because it helped separate a bit the problem. You didn't have to understand everything at the same time, but also the reason why it took a bit of time to understand the issue with mixing and how this could modify the properties of the interaction through the weak interactions of the quarks. And so actually, so for instance, currently you had something, so not very surprisingly, so you see that here you got, so VUG, VCS, VTB, which are very close to 1. And the departures, for instance, for VUS here, so that means that actually the C's are going to be close to 1. And when you look at the actual number, and we're going to discuss a bit in more detail how you can get them. So S12 is actually 0.2, so it's not negligible, but S13 and S23 are very small. Delta is around 60 degrees. And the idea that was introduced in particular by Wolfenstein was to use this hierarchy to find a better parametrization, better in the sense that you try to have order 1 parameters rather than very small and very large parameters. The idea being that not only is it hierarchical, but the fact that when you move, so if you just try to crosstalk with 2 neighboring generations, the effect is suppressed, but it's even worse when you try to talk between the first and the third generation. And so that meant the idea of trying to implement that by using S12 or equivalently lambda as an expansion parameter. In order to achieve this simpler parameterization. And so you can do that actually, you can define that quite easily. So you, as I said, you start from the fact that you want to do an expansion in this off-diagonal element. And so you define lambda here as being the term defining the size of this term. And then you're going to define, you're going to define other parameters that will be able to parameterize.
Sorry, what is in the numerator for lambda squared?
VUS, sorry, VUS over VUD squared plus VUS squared. And so here for the second one, you've got a squared lambda 4, VCB squared over VUD squared plus VUS squared. And so if you have this, so S12 is lambda, S13 is a lambda squared. So you see that already here you're using a suppression of a power of lambda in order to say that S13 in practice is smaller than S12 if A is of order 1. And then the last piece that you have is actually a piece that will correspond to defining the phase, because for the moment I've defined only members terms with respect to modulize of the CK matrix elements. So I need something that will be a phase. And so for the moment, so you have VUG, VUB star over VCD, VCB star. So what you can do when you have that is that you can just use unitarity of the CK matrix in order to define or express all the matrix elements, the CK matrix elements, in terms of these 4 parameters. And so when you do so, and you afterwards you expand in powers of lambda, so you do the additional thing of expanding in powers of lambda. What you find is actually a structure which is quite simple. So you've got things that are of order 1 in the middle, So I'm going to do the expansion up to lambda 4. So you have 1 minus lambda squared, or 1 minus lambda squared, 1. Then you got lambda minus lambda lambda, and then, and that's probably, I should probably do it this way. You've got a lambda to the cube rho bar minus I eta bar, a lambda to the cube 1 minus rho bar minus eta bar, minus a lambda squared and a lambda squared. And you see that here, by what we've done is to re-express the Decay matrix with a clear structure, hierarchical structure that is present. And so obviously, as I said before, this is a representation that makes sense and is useful because we know something about the relative size of those various matrix elements. You also see that at the level of the expansion, you do have 2 matrix elements that are carrying the part related to the imaginary contribution of the CK matrix. So eta bar here is going to be related to CP violation, because imagine that I put eta bar to 0, then my matrix would be completely real. So no CP violation anymore. Lambda is related to the Cabibbo angle. And so the point is that I stopped at some order in the lambda expansion. Obviously, I could go higher, and what would happen then is that, and you can find papers where this is done. It's not complicated. It's just tedious. You would see that actually the eta bar, so this imaginary part, would also pop up at higher orders in lambda in the other matrix elements. So it's only that at the first order at which this phase appears is, so it's appearing at VTD and VUB at leading order, not first order. So these are the first matrix elements to feature eta bar in the expansion, but they are certainly not. They're not the only ones. Just to make sure that this is clear. But their contribution will be very much suppressed. So you can think of them, all the other ones, as being real at the beginning. Okay, so the fact is that so you know that eta bar is related to CP evaluation. Actually, you can define a quantity that will assess this amount of CP validation in a basis independent way. Because here eta bar is just because related to the definition I've chosen of my 4 parameters, but actually you can introduce an invariant, so a quantity that is going not to depend on this kind of definition, which is called the Yellowskogen Variant from Cecilia Yellowskog. And the idea is that you take the combination, a product of 4 matrix elements. I'm sorry, I should write it properly. So you take 2 matrix elements, and then you swap the indices, and you take the conjugate. You take the product, and actually you can show that this quantity is going to be the same for any choice of I, J, K, L that you make. So it's proportional to this J, and then you've got something which is just a pure a structure function, if you wish. In particular, you see that you've got constraints about the fact, so you have to be careful, because if you're taking any ijkl, in some cases that will be 0 equals 0 because of the epsilons. But at least for the ones that are not just trivial, you will get the same J. And actually, when you in practice, when you look at the two parameterization we've chosen, J, you will have it as either a product 1, 2, 1, 3 sine of delta, or equivalently, it will be lambda to the 6 8 square eta bar. And so that shows you that it is indeed something that will be different if there is CP violation. It depends. So, okay, so it's really CP violation. If J different from 0, as I said, then it depends on all the mixing angles. And you can see that more easily with the first expression using this kind of Euler type parameterization. And the last thing maybe that is interesting with this first representation is that J is small because of the mixing angles, not because of delta. So that means that if it's this the value that we'll get, and which is suppressed because you see there is a lambda to the 6 power, so it means that J in practice is very small. It's small because of the various moduli. It's not because the phase, so the amount of CP violation in itself, or the phase corresponding to CP violation, is small in itself. So that means, and that will be something that we'll see later, that you will have to look for processes that might be a bit suppressed, but the amount of, if you look for CP violation, but the amount of CP violation that we will find is large once you've selected those processes. So now we can go to representations of these various various parameters. So the idea is that actually, so you've got these 4 parameters, and you can try to determine them, but obviously it's a bit complicated to represent all the various aspects of this parameterization. So the starting point that has been very useful is to say, okay, I can try to show relations or use the fact that there are relations between these parameters inside the CK matrix, because, yes?
Sorry, I cut you, but I couldn't hear if you were hearing me. I just didn't catch the name of the person of the above definition.
Yellowskog?
Yellowskog?
Yellowskog, that's Swedish.
Okay, thanks. Thank you, sorry.
Cecilia, actually. Very nice person. Okay, so for the unitary triangles, so as I said, so you start from unitarity, which is quite natural, of the CKM matrix. And so that's the same thing that we already used when we were discussing the number of parameters, independent parameters that you have inside the CK matrix. So you can say that I should have VV dagger, which is delta ij. And so we're going to use, we can think of writing these relations, choosing specific values for I and j that are different. So actually, this way you got 6 relations that you can write, but I will focus on 4 of them. So the idea is that you take either two columns or two rows of your CK matrix, different one, and you write the product. And so what you will get, for instance, if you're choosing two terms that differ to two entries that differed by the B or the D entry, you can write this kind of relation. Same thing if you start playing with VUS, VUB star, VCS, VCB star plus VGS, VGB star. And then, so I'm not going to write down the top one, the one involving tops. I'm just going to write those ones. GPTS star and CU. Okay, so why did I choose to look at those ones? It's because when you think in terms of the, if you want to write down relations that are likely to be of interest for when you're dealing with external states, you will not have the top one. Obviously, in some cases, you will need relations involving the top one, but the idea is that you focus on relations that will, and we will see later that it is the case, that can occur naturally when you're discussing the decay of mesons that are made of BD, BS, SD, or CU. So that would correspond to the BD meson, for instance, the BS meson. Here that would be the kaons, and here that would be the D meson. And the fact is that when you look at the size of the various, so these are relations that you can write as triangle in the complex plane. Various triangles, and when you look at the side of your triangles, actually you see that in terms of the power of lambdas that are involved, the first one you got lambda cube, lambda cube, lambda cube, but the other ones actually have different sizes for the various sides of your triangle. So that means that you've got the so-called BD triangle, which is small, but with non-squashed, if you wished. Whereas the other ones are squashed with various large and small sides. So if you wish, the BD triangle is well formed. It looks really like a triangle. It's not just some kind of very elongated triangle, but the sides are small. And so actually the thing is that it turns out that in relation with what I just said before, the fact that if you want to look for CP evaluation, you prefer to have some kind of representation involving some elements where you see clearly that there are angles, there are faces present, large faces, even at the price of having small sides, and so rare processes, but with significant CP violation contributions. And so that's why generally the BD triangle has turned out to be a very useful tool to represent and analyze CP violation. And so that's why it has considered as being the unitary triangle. Before you had various unitary triangles, but this one is the unitary triangle, actually the one that people are using is a rescaled version of that. So you just take this relation here, but actually you rewrite it by normalizing actually to VCD, VCB star. And so in the end, you get something which has this shape. So you have from 0 to 1, and then you can represent the one of the two other terms of the sum that I've just shown before, VTD, VTB star over VCD, VCB star. And then you got the other side, which is VUD, VUB star, sorry, over still the same normalization, VCD, VCB star. And when you do that, because of the way we defined actually the various matrix element, and that's why we have this funny way of defining eta bar, it turns out that here the apex of your triangle is exactly rho bar plus I eta bar. So actually you do have a representation using this triangle that gives you immediately the value of eta bar, which is the term of interest for the analysis of CP violation. And then, because we're interested, I said that the fact that you have eta bar different from 0 is a sign of CP violation. That means that the fact that you have angles in this triangle that are different from 0 pi is also a way of assessing CP violation. So that's something that's going to be important. And so we just define them. So there are as alpha, beta, and gamma. So these are just the various arguments of the, so you just take the relative sides of the relative positions of the various sides. So that's going to give you alpha being the argument of VTD, VTB star over VUD, VUB star, beta being the argument of VCD, VCB star, VTD, VTB star, and gamma being the argument of VUD, VUB star over VCD, VCB star. In the literature, you do find a different convention. Actually, you have also a convention with phi's that are present, and obviously, since nothing is simple, alpha, beta, gamma is phi 2, phi 1, phi 3. Otherwise, there would be no point. Actually, the reason for these two conventions is historical, mainly. It's because at the time where things were designed to analyze CP violation in the B quarks, after much longer after it was discovered in the Keon system, you had two competing experiments working on this, so-called B factories, producing a very large number of Bs through the decay of a resonance called the BB bar resonance called the epsilon 4s. And so one of them was in the United States near San Francisco, and so at Stanford. So that's the alpha beta gamma convention, whereas in Japan you had the Bell experiment at Tsukuba, not very far from Tokyo. And the point is that they decided at the beginning to fix the notation, and they didn't confer and chose different conventions. And so that's why we keep on having those two set of conventions. I will keep the alpha beta gamma convention for the time being. But that explains the reason, historical reason, so to speak, for these different conventions. Okay, and so now if we want to, so obviously when you do this kind of representation, you have also, so that's nice because you've separated somehow the problem between the determination of A, which is related to a VCB, lambda, which is related to VUS, and the question which is more related to CP violation. But obviously when you deal with the determination of the CK matrix as a whole, you have to do the determination of everybody at the same time, naturally. And so that's why you, if you want to determine the 4 parameters of the CKM matrix, then actually you will have to try everything at the same time. So you want to have an access to the moduli, which is also, even if I said that this representation of the unitary triangle is focusing on CP violation, you still have the lengths, the relative lengths of the various sides, which are also giving you information, obviously, on the moduli of the CK matrix. So these are the sides of the triangle, among other. As I said, you have also additional information. And so that's typically things where you will look at the modulus of VUD. And clearly, the easiest thing to do for that is actually to try to go back to what we discussed yesterday, leptonic or semi-leptonic decays. So with charge currents. Why? Because we saw that we were able to discuss the hadronic part, which was not very complicated to deal with. And then you have an operator where you have quarks on one side, which will give you directly VUD. Then you've got the leptonic side of the operator that will be immediate to deal with. And so this is something that is the most appealing set of decays that you can imagine in order to access those pieces of information. One point is that this will not be possible for the VTD, VTS parameters. I'll come back to that later. VTD, VTS terms. But it's you can guess already that the fact that the top quark does not hadronize and decays very quickly and overwhelmingly through a big quark means that actually you don't have many handles in order to determine the decay of the top quark in very light quarks. It's a difficult experimentally speaking. And then, in addition to the moduli, so the sides, you have to access the angles. So that's related to CP violation. Sorry. And then for this, so you will have really to look at CP asymmetries. So to look to a process, the CP conjugate, and see if there are differences between the behaviors. And actually, it's not the other part. And so afterwards, at some point, actually between the moduli and the angles, I will discuss the fact that you have another kind of observable that is also useful, and another kind of processes that is very useful in order to extract information on the scale matrix. And the fact that you have what is called neutral mesomixing. The fact that actually the mesons I've just mentioned here, which are neutral mesons, BD, BS, K, and G, can actually mix through weak processes into their antiparticles. And that's allowed. That's a rare process, but that's allowed. So that's something that, since it's governed by weak interactions, give you also additional information, and actually will give you information especially on VTD and VTS. We'll see that in the floor. Okay, so now I'm going to give a few elements, not many elements, but a few elements for the various ingredients. I will try to focus a bit on some aspects on why we're choosing some of the processes, and why we believe that we have a good handle on the various hadronic uncertainties in particular. So anything related to the strong interaction in the non-perturbative regime. But so that will be, so for the moment, as I said, I will start with the moduli of the CK matrix element. And as I said, most of the time that will be leptonic, semi-leptonic decays. That will be the name of the game. So if I start with VUD, so one thing which you can think of quite easily is actually to take the pion beta decay. So that's very simple. That's pi plus decaying into pi 0 e plus nu. And the fact is that, so you can do the same as analysis as we discussed last time to say that the branching ratio is actually related to the matrix element that I can parameterize in terms of two different form factors. So you have only the vector contribution because we're looking at something which, if you apply parity, would give you would show you that actually the actual part cannot contribute on the hadronic side, and so you can use the Lorentz decomposition in order to separate into two terms. Last time I introduced F0, so F minus is just related to F0. In this way, so actually it's plus. So these are just two different conventions, and depending on what you're interested in, it proves more practical to use one or the other. And so the thing is that actually, when you look at this, so in principle, you need to have information on F plus and F minus and the variation with Q square. So that's not a completely trivial thing. But actually, one thing that you can think of is just to see if there is a limit where you control better what's going on, so that you don't have an arbitrary number to start from. And then one thing which is natural is to look at what's going on in the isospin limit for the form factors. And so actually you see that if I were to look at the isospin limit, actually what matters is F plus. You have a suppression, F minus is suppressed by the masses, the difference of masses. And moreover, if now you're saying Q square is never going to be very large, so maybe it's interesting to look at F plus at 0. Then you have the situation where you can, so you're looking at pi 0, P, d bar gamma mu u pi plus P. And then you can relate that through isospin, for instance, to the third component of the vector current. And so this is actually just counting the number of U and D quarks that you have, valence quarks that you have in your pi n, putting a different value for the U and the D. So in the end, that's telling you that this is normalized to be unity. And then, so in the isospin limit. And so now that's very nice because you do have a starting point. It's not that F plus is something which can have any kind of value. You know that it has to be close to unity with departures when you've got Q squared different from 0 and when you've got the isospin, which is broken. And so you can check actually, evaluate the corrections to that and determine whether, and use this information to extract VUD from the measurement of this branching ratio pi plus to pi 0 e plus nu. So the problem, so that means that it can be used to extract VUD. The only problem is that it's the rate of this process is very small. And that's due to phase space. It's because the value of the pi plus and the pi zero are very similar, and that's exactly the reason why we introduced isospin at the beginning, to try to analyze what is going on at the level of the form factors. But then that has the drawback that since you have very little space for the decay, that means that the branching ratio is something of the order of 10 to the minus 8. And so experimentally, that's quite challenging. So you do find constraints on VUD from this process, but it's actually not a very simple one, not a very powerful one. So the second thing that you can imagine to use is to go to, well, more, to increase a bit towards the nuclear aspect. And so to look at the neutron beta decay, which certainly is not a rare process. It's something that happens certainly easily. The point here is that, so contrarily to what we had before we had only a contribution from the vector current here. Here you've got, when you're analyzing in terms of matrix elements, you will have contribution from both the vector and the actual part. Because if you're, the reason for that is that if you try to analyze in terms of parity, you can use parity, but the problem is that parity will affect the spin of your neutron and your proton. So that means that you cannot connect the same matrix element. It will connect matrix elements with neutron and proton spin orientation being different. And so that means that in the end, you cannot show that something is equal to its opposite and is zero. In these cases, both V mu and A mu contributions do occur. And so actually you can define two different quantities, two different matrix elements that will be proportional to the vector and the actual component of your neutron decay. And then it turns out that even in practice, the two contribution cannot be are of a similar order. They contribute similarly. And actually, when you look at the branching ratio, they will have a structure which will be something like VUD square 1, so it's proportional to VUD square times 1 plus 3GA squared. So the accuracy of your determination of VUD is obviously related to the accuracy of the determination of GA. And there is, so there are some issues which are related a bit to the value of GA, but more to the value of the branching ratio. There are different measurements that are not agreeing completely well concerning the neutron decay, and that means that this, for the moment, so are sources of uncertainties. So bizarrely, for VUD, and that's why I'm spending a bit of time also, because there is currently a bit of controversy on this. What you would like to go for VUD, contrary to what I indicated at the beginning, is to go for the more complicated stuff rather than the simpler stuff. And that's nuclear beta decays. So really nuclei, not nucleons. The point is that you obviously, if you wanted to, so in principle, it is proportional to VUD. Now, if you're taking any kind of nuclear transition, that's going to be extremely complicated because you need to understand things concerning the strong interaction in a many-body system. So it's very, very challenging. And the accuracy, in principle, would be difficult to assess at the same level as the processes I've shown before. The situation is a bit better, actually, because you don't take any arbitrary nuclear beta transition. You are using what is called super allowed transitions. So that you look at transition for n to n prime in U, where actually the state in which you start and the state when you finish is just the lowest possible concerning orbital momentum. And so why do you do that? It's because then you're in a situation where only the vector part of the transition matters. So you can show again that the only ingredient you're interested in is this one. You can still play the same game as before, and I'm not going to rewrite it again, but to have two different factors, which are f plus and f minus, still depending on q squared. And actually, you can again use isospin symmetry arguments to show that f minus does not contribute in the isospin limit. And that f plus can be expressed purely in terms of isospin numbers. So the idea is the same as for the pion. In the case of the pion, I was able to relate by isospin to something that would tell me that f plus at 0 is 1. Here, because these are nuclear objects, so you obviously have questions of isospin that are far less trivial than what you have for the pion. But so in the end, f plus at 0, you can show that you can relate it to a matrix element between a nucleon and a nucleon, the same nucleon, with a combination of counting operators that will give you just a pure isospin number. And then obviously you have to worry. So this allows you to have a very simple expression for your two form factors at 0 in the isospin limit, and then you have to compute the departures from q square equals 0 and isospin limit. And actually, so the point is that you can do that for all the decays of nuclei that follow this pattern. But then, so that means that currently you've got something like 15 different nuclear decays of various nuclei that are considered. So it's really ranging very different atomic numbers that are considered. But the point is just that you go from 0 to 0 in terms of orbital momentum. And then there is a good overall agreement in the extraction of the UD, and already that's quite an achievement. That means that not only the isospin limit that I've discussed just before is appropriate and gives you a good result in general, but also that you have a good mastery of the corrections up to a certain point, because for the moment there is not a complete consensus concerning some of the isospin corrections to be applied. And so that means that you have values that have decreased a bit for VUD, and that currently are not in perfect agreement with the rest of the fit. It's not, then the question is, by how much is it in disagreement? And obviously, depending on how you're treating your uncertainties and also you're performing this evaluation of these isospin corrections, you do have slightly different assessments of the uncertainties. So that's currently debated, and people are arguing. So I'm not going to give you all this detail, but currently there is some level of disagreement on the disagreement, but probably this will be solved in the coming years. Okay, so I will be much quicker concerning the other moduli. For VUS, you can think of using a similar decay, k2 pi nu. So here you will play the same game. You've got f plus and f minus. The point is that f plus, sorry, you can have the same kind of argument that it should be 1 at 0, but this time it's not the isospin limit, it's the SU3 flavor limit that you have to consider, where you put the strange quark at the same, you neglect the differences between the strange quark and the U and the D quark. So this is obviously not necessarily intuitively a very good limit, because you do have the question, but first you have to ask yourself, compared to what? And so typically you're neglecting the difference, for instance, between the D and the S quark compared to the typical GV scale of strong interactions in that for these hadrons. And then you have to take into account the corrections to that. And so you would say naively that there are something of the order of 20%, 20–30%. Actually, they are smaller, because there is a theorem showing that actually the corrections are going like not like ms over md, but ms over md to the square. So that's the so-called Ademolo-Gatto theorem. And so that means that actually they're controlling the corrections to this one quite well. Here, F minus is actually kinematically suppressed. And so you don't have to take too much care of that. And so that means that actually k2 pi nu is a very good way of getting information on VUS, because you've got a very good control. On top of that, now you've got a very dedicated lattice studies for the form factors that confirm the validity of this general picture and allow to compute very high accuracy corrections to this, including electromagnetic corrections. Then you do have a bunch of leptonic decays here, or you have also the possibility for the heaviest of the free leptons, the tau lepton, to decay actually hadronically. Oh, sorry. And so that means that it's the other way around. It's not the kaon decaying in the tau, but the tau decaying into the kaon. That's completely possible. I mean, you just have to make the W and then US, and you go into a kaon. And as we discussed last time, all three are related to the kaon decay constant. And once again, due to the simplicity of these processes, you do have competing information from both k2 pi and k2 mu nu, k2 e nu, and tau to k. So the only thing is that the level at which, I already said that before, the level at which we are now concerning the corrections, the accuracy of the computation, is that the issue of the electromagnetic corrections start being very important. Given the accuracy of the QCD part. So we're talking precision that are to the per mil, and so obviously you start worrying that the initial assumptions that I already indicated, that I'm neglecting, for instance, a photon being exchanged between the leptons and the quarks, are not important, and so on. Here we start entering a precision regime where this is not true anymore, and you have to take into account those electromagnetic corrections. Okay. VCD, VCS will be a much simpler affair. So because actually the main element of information is just when you're looking at mesons that contain a charm. So CD or CU, actually that's CD here, not CU. CU would be neutral and couldn't decay electronically. So CD and CS, so D plus, N plus, N plus, N plus everywhere. So these are the ones that are really giving you information that is reasonably accurate. In principle, you could imagine to have access to look, so these are the main source of information, accurate information. For the moment, semi-electronic decays like D2Pi or D2K are accessible, but not competitive yet. But not by far, so that's going to happen soon. You had earlier ways of determining those quantities from so at earlier times there were determinations, for instance, from observation of W bounds that you had, and W decaying into a C and S at LEP. And then the charm and the strange being a jet that you have to identify. For the same, so that would be for BCS. You had also neutrino nuclear reactions, where you would be able, after some heavy gymnastics, to extract some information on BCD. I'm not going to spend time on this in detail because actually they're now quite outdated. So that's not really something that requires a lot of discussion for the moment. Okay, so that's for the first two rows and columns for the moment. So we had VUD, VCD, VCD, VUS, VCS. So you saw that at the beginning, the idea was to have some, use some symmetries, especially isospin or SU3 symmetries, in order to be able to say something, at least a reasonable approximation of the form factors. Already when we are moving to VCD and VCS, I didn't mention that anymore. Actually, here I just assume that we have some information on the FD and FDS decay constant or the form factors, which is true. And you're in particular able to get information on the lattice using lattice QCD quite easily, because the kind of energies involved are the right amount. So it's not too small, not too large. So in the end, you do have accurate numerical computations using discretization, putting the QCD in a box. Now, when you're moving to VUB and VCB, that's a slightly different story. And so I said VCB and VUB, but actually I'm going to spend a bit of time on VCB here. So it's not really possible to imagine doing something with the leptonic transitions, because that would amount to say that you want to have something like a meson containing a B quark and a charm quark decaying into leptons, and that's BC quarks, BC mesons, sorry. BC mesons are actually very difficult to get. You do find a few of them currently at the LHC, because you're producing in your PP collisions. You do find in some cases a B and a C bar that you can put together and analyze, but the production rate is very low. And actually, if you look at the branching ratio of this kind of decay, it's very, very small. It's very much suppressed compared to the rest. So it's not really something that you're going to be able to analyze in the foreseeable future. So you really have to look at B2C nu in semi-electronic transitions. No way out. And so you can imagine actually two different things. So the first one is what we've been doing up to now. It's to start from a state containing a B quark and then going into a state that contains a charm quark. And so, for instance, the simplest version of that would be a B meson going into a D meson and nu. You can imagine to play with various things when you start this way. You could imagine, for instance, taking an excited state of the D meson. So, for instance, a spin 1 meson, D meson, it's spin 1 charm meson rather than the spin 0 charm meson. You could imagine also to do the same thing, not with mesons, but with baryons. So you take, for instance, a lambda B that contains a B quark, and then it goes into a lambda C. You could imagine other stuff. You can imagine, for instance, a BS going to a DS. So this time you start with a BS combination that goes into a CS combination afterwards. And all this, it's exclusive decays. Why do we say exclusive? Because we say that we're specifying everything concerning the initial and the final state. So in this sense, it's exclusive. So in practical terms, if you have producing, for instance, copiously B mesons, you're selecting in all your collisions, all your processes, only the ones that have in the end given you, for instance, a D meson and nothing else, and you're forgetting all the rest. The other possibility is to do something where you're actually a bit less picky about what you want in the end, and you say, okay, I still start from a B meson, but then I take anything that contain charm. So as soon as, so I get kind of a B with plenty of different outgoing particles, as long as the total amount of charm in the end is 1, then I keep it. So that's a different way of proceeding. Why do we consider this alternative possibility? It's mainly because we have the idea of that summing over a large number of hadronic states can be said to be more or less equivalent to considering the process at the quark level. And I will express that in a bit more detail afterwards, but that's why so that's this idea of quark-hadron duality. And that's an idea that clearly cannot fly very much if you're looking at lighter quarks, because if you say that you need to sum over a large number of hadronic states, then clearly if you're looking at a kaon that can decay only in a pion and nothing else, that's not really the good conditions in order to start applying these ideas. On the contrary, if you have a heavy quark like the B quark, so B meson decaying in quite a large number of different states, then it potentially might be okay, and that might be of some interest. So I will discuss briefly both possibilities. So actually, I will just focus on B2D and B2D star and nu. And so the thing is that you do have, in principle, as I said before, information on the form factors from lattice QCD, but only for low recoil. And so that means that you do have And actually, that's a small region of phase space because the difference of masses between a B and a D or a B and a D star is quite large. So that means that when you're at the endpoint of the other endpoint of the spectrum, when you've got a large recoil, actually, it means that your D has quite a very significant energy. And so it would be very, very much not suited to the discussion of lattice QCD in general. So one tool that is used in order to try to analyze what's going on, and that's both for lattice QCD, but also more generally when you're dealing with the form factors, is actually to try to use another symmetry to simplify the problem. Once again, you have a starting point to discuss the form factors. So once again, at the beginning, when we were discussing VUD, I told you isospin is a great tool here, and we can show that we know something, at least there is one point of this form factor that is known. So this f plus of 0 equals 1 in this isospin limit. And so we can work around corrections to that, but at least we know where we start from. And so the idea is a bit the same here. Obviously, that's going to be a very different limit. Actually, that's been the opposite one. Isospin would be just neglecting the light quark masses compared to the typical lambda QCD scale. Here, that's exactly the opposite, is to start saying that MB and MC are very large. Well, actually, they're actually large compared to lambda QCD. This is certainly something which is correct for MB. For MC, you might discuss a bit more whether it's accurate or not. And actually, there is a bit of discussion concerning the real accuracy that you can have, but at least it's giving you an idea of the starting situation. What are the actual form factors that are relevant? How can they be expressed, and so on? So what is actually the situation when we are doing this? So the idea is that you can build an effective theory that will embed this idea of a very large MB and MC. So that will be the heavy quark effective theory. And so the main picture, if you wish, is that you think of your system, of your B meson, as being a heavy quark, a light quark, which is somewhere around. So it's a bit hydrogen-like, if you wish, with exchanges of gluons. And so the idea is that, so it's a bit an hydrogen-like situation, obviously with a color rather than strong interactions rather than electromagnetic interactions being involved. But the idea is that the light quarks interact with the heavy quark through soft gluons. You don't have the exchanges of, because it's a situation where actually the interactions of the gluons, it's just giving you the difference of mass, if you wish, between the quark mass, the heavy quark mass, and the heavy meson mass. So it's all the interactions have to be through light with soft gluons. And so you have you can use the fact that also your gluons have typical energies which are much smaller than the mass of your heavy quark. And so what's happening is that in the end, and I will show a few elements of that, the general picture is that in your B meson rest frame, the B quark is almost static. And it's a source of soft gluons. And actually, what I will show very briefly is that in this situation, actually, you got a decoupling between the various degrees of freedom. And in particular, that means that the properties of the heavy hadron are independent of the spin and mass of the heavy quark. So that means that actually the way the gluons are sent do not depend on the way the relative orientation of the spins between the heavy and the light quark. So that means that actually you will have a huge simplification in the description of the structure of your B meson, because it has to be invariant if you're changing the spin orientation of your quark, your heavy quark. So for instance, that means that if you're looking at the D0 and the D star 0, or the D and D star, just spin 0 and spin 1, they will have very similar properties, because actually they're just differentiated by this orientation of the spin of the heavy quark, so that you will be able to connect the informations concerning and dynamics concerning the D and the D star meson in this limit where you send the charm quark mass to infinity. So what time is it? Okay, I can just outline very briefly how that works in practice. So you have your heavy quark, which has a momentum which is not very far from being the one of the B meson. So as I said, in the rest frame, the heavy quark, in the heavy meson rest frame, the heavy quark is almost static, so it's flying the same way in a general frame, so that V mu is just selected by the B meson. So you see that indeed P mu and PB mu are almost going the same way. And then the residual momentum K is actually of order lambda QCD. And then if you look at the propagator of your heavy quark, and you try to use the fact that you've got this kind of decomposition, then for simplicity, so that we can do the separation more easily, I just multiply by P slash plus MQ. And then I put in information that I have concerning the expression plus K squared, sorry, plus K squared. So in the numerator, I just put exactly the expression of P that I have before. And in the denominator, I just use the fact that I have, I know to express that in terms of this velocity V and the residual momentum K. And then if I'm just using the fact that I believe that during the interactions, K squared is small compared to VK, because one is going like lambda QCD and the other one like lambda squared, then I end up with this simplified propagator. So you see that here you have a projector that we can call P plus. You can have the opposite projector P minus. Oops, sorry. Okay, here. And so you see that there are already simplification, and we can use the fact that this propagator involves P plus here to say that the interaction with gluons are going to be also quite simple. You will have, so in general, you should expect to have something like IJS gamma mu TA, but since you've got P plus arising before and after the interaction with the heavy quark, then you can look at the result of the applying P plus on gamma mu, and actually what you find, it's not very difficult to check, is that the only thing that remains is V mu. So that means that actually everything related to spin has disappeared here compared to the gamma mu matrix that you had at the beginning of the interaction. So no spin information. So that's what I was just explaining, and you can put that into an actual effective theory. You can actually write down, say, okay, I'm just defining the relevant degrees of freedom of my theory that are going to be a projection of my heavy quark, or heavy quark field. This is just a purely kinematic term to remove MBV mu that is present everywhere and keep only the residual momentum. And you can write down a Lagrangian starting from the QCD Lagrangian that will be a Lagrangian that will involve HV up to corrections of higher orders in lambda over MB. And as I said before, the fact is, that's exactly what I mentioned before. You see that actually the spin of the heavy quark doesn't play any role in this theory anymore. And so that means that you can have, you have a spin SU2 symmetry in LHQET that actually allows you to, as I said before, relate and simplify a lot the discussion of the form factors. Because actually what will happen is that even though at the beginning, when you're looking at the form factor, the current you're putting is going to select a very specific configuration of your spins at the beginning and at the end of the process. The fact is that in HQET, we're saying that if you're looking at a B and a D, actually most of these questions are irrelevant and all the configurations have the same behavior. So whether we're choosing a current or a different current is going actually to give you something which depends on the same heavy quark dynamics. So in practice, what does it mean? Is that it means that you have relations between form factors in this limit. So as an illustration of that, if for instance, I'm taking matrix elements, so once again, that's the same thing here, F plus. So here I'm just writing again our old friends, the form factors for a pseudoscalar to pseudoscalar for a vector. But then, as I hinted at, you can also look at what would happen if you have a D star. And then, as we said before, you do have many more possibilities in terms of Lorentz structure. So that's why you have more form factors in principle. So some of the scalar factors in front here are just for convenience when you're doing analyzing, doing some predictions in terms of those. So that's why they have become quite customary to use this kind of decomposition, but I just write them down for the sake of completeness. In practice, the only thing that matters is the number. So here you see that for the actual component, for spin 0 to spin 1, you get 3 form factors. Whereas if you're looking at, I forgot the B here, C bar gamma mu B for the vector part, there is only 1. And actually the fact that in one case you got something which is a scalar and the other one is pseudoscalar, you've got the epsilon that is present, that is related to the parity properties of the various ingredients of the matrix element. Sigma V. Yes. So as I said before, you've got F plus F minus on one side, A0, A1, A2, A3, and V on the other side, all of them being functions of Q squared. So in general, that's going to be complicated, but in practice, because of these simplifications that you have at the level of the interactions of the heavy quark with the rest of the system, actually you can find a lot of simplifications. In addition to that, so you analyze your process as being just at rest, this kind of structure, and then imagine that you have this decay occurring. So you've got a Q prime. If you were in the situation where in the no-recurrent limit, so Q is typically B here and Q prime is C, in the no-recurrent limit, then you would have no changes between the two situations. So it's a no change before and after. So actually, that's telling you, and you can prove that probably in the no-recurrent limit, there will be a normalization that can be done easily. Because actually you're doing somehow if you think in terms of quantum mechanics, you're doing the analysis of a system, a transition between a state and the same state, so to speak, because from the point of view of the effective theory, they're identical. So very probably that's going to be the same situation as what we had before concerning using a symmetry like isospin and considering that at some kinematic point it's 1. So certainly the no-recurrent limit is the equivalent of that here. And if we consider the system in the no-recurrent limit and the transition in the no-recurrent limit, since there is no change before and after, you've got a perfect overlap in the situation before and after. And so certainly you will have a normalization accessible at this particular kinematic point for the reduced form factors in this large this heavy quark limit. And then away from the no-recurrent limit, I forgot to say the recurrent limit that would correspond to V equals V prime, since we're defining everything in terms of the situation with respect to velocity of the mesons. And so if we are away from the no-recurrent limit, then you will start having, when you go from one situation to the other one, soft gluons being exchanged between the final heavy quark and the light quark, so that there is a reorganization of the structure to come back to the D meson, in this particular case, starting from the B meson. So that means that certainly there is a less overlap between the two configurations. So probably there will be there is less overlap between the initial and the final configuration. And so that's why very certainly you will have a decrease in the form factors. And so in practice, what's happening is that when you implement these ideas, so this heavy quark effective theory, and you look at the consequences of these SU2 spin symmetry that allows you to change the orientation of the spin of the heavy quark without changing the actual interactions that you have with the rest of the system, you end up with finding relations between those various those various form factors. Actually, all form factors can be described through a single reduced form factor. So that's was proposed by Isgur and Weiss. So that's the Isgur-Weiss function. And that depends on Q square, but if you prefer, you can rewrite that in terms of V dot V prime, so the product of the velocities. Since we saw that the situation where you have zero recoil, so V equals V prime being 1 is important. And so what you have is the fact that the same Isgur-Weiss function allows you to describe all the various form factors. I forgot to put a -1 here. And I insist. So here we're relating form factors for two different final meson, one with spin 0, the other one with spin 1. And we're saying that in the limit where MC and MB go to infinity, all these form factors are described by the same reduced form factor. This is the Y function. And on top of that, you do have what I just discussed before, the fact that the no recoil limit, because actually from the point of view of you're changing in this limit of no recoil with MB and MC going to infinity, you're changing the flavor of your quark, but you're not changing anything else. So the overlap between before and after is perfect. And so that gives you a natural normalization. And so when you do the computation, you see that the definition of the Isgur-Weiss function makes it very simple, means that it's 1 at no recoil. And so you see that equivalently to before, you have a situation where you can start from in order to discuss the value of the form factors. Then obviously you have to discuss the corrections to that, and that starts being a complicated subject. So I'm not going to, now that I've given you the idea here, I can just say that for B to D nu and B to D star nu, you can express the decay rates as functions of psi plus corrections to be evaluated. And so that's things that can go depending on a situation like lambda over MB or lambda over MC. Actually, it's slightly better for the B2D case. For B2D, because actually you've got some kind of equivalent of Ademo-Logato theorem. That's Luke theorem that is actually telling you that the corrections are not as large as lambda over MB or lambda over MC. They're actually, sorry, it's for B2D star. It's actually that it's going like the square. So that means that you're better protected against this kind of corrections for B2D star than B2D. On top of that, phase space tends to be more suppressed for B2D. So that means that even though in principle, from the lattice point of view, B2D is easier to handle than B2D star because the D meson is a ground state, whereas D star is an excited state, and it's complicated to get an information on this, more complicated to get information on this. In practice, the situation is a bit more equal, I would say, concerning the determination of VCB from the those two point of view. And the last element, so you use lattice in order to get information on 2D nu, B2D star nu, plus the fact that you have this information from HQET that you can use to constrain your fits in order to help determination at low recoil. And then you can use tricks that we discussed last time, like this idea of Z expansion to extrapolate to the world phase space. Because I remind you that here what we're discussing is a situation where we really like for B2C transitions the low recoil for different reasons. You got information on the lattice for this one, so you have to state low recoil, but also the discussion I just mentioned before concerning the application of HQET. You also want all the physics to remain soft. So you want all the energy, the difference of masses between the B and the D meson to be taken away by the lepton pair. You don't want it to stay around and be used by the quark degrees of freedom. So that's why you have to do the extrapolation afterwards from the low recoil region in order to extrapolate to the world phase space. And this actually has been an issue because there have been various implementation of this extrapolation. And actually with more or less assumptions inside. Why was it so? It was because at the beginning you didn't have so much, you didn't have so many data points, you didn't have so much information from the lattice, so people tried to add elements to help the extrapolation to be performed. And this was not necessarily a good idea. So in the end, trying to compare with the data, people realized that it was not necessary to make so many assumptions on this, and that actually induces some differences in the extrapolations that are performed. So that means that in the end, the extraction of VCB depends still on the type of extrapolation chosen. And so in the literature, you will find various values that are a bit dependent on how you perform this extrapolation. One thing that I should mention is that so here that's low recoil. So v dot v prime close to 1. But you want to extrapolate because so the phase space suppression that I was mentioning is actually near the endpoint. So that means that actually you've got more data far at large recoil. And so that's why you really need to put together information from both low recoil and large recoil in order to be able to extract VCB here. Okay, so another way of performing the same kind of analysis of VCB, as I said, it's the inclusive version. And so, as I said, the idea is that you compute, you take with you anything that contains a charm, but you're not selecting exactly what you want. And so what you can do is to say, okay, why would I do that? It's because actually this summation, if you do really the summation over everybody, is going actually to be quite interesting from the theory point of view. That might at least at some level give you the feeling of a simplification. So I'm separating the hadronic part and the leptonic part. I multiply by the phase space corresponding, well, that's really it's the whole phase space, not only the phase space. Okay, so the phase space, you've got the leptonic part, which is once again very simple because it's just the solution to the Dirac equation. And then here you've got the current that is needed. And since we're summing on anything, then it's really the vector and the axial part that are both contributing. There is no way out. Okay, so now I can just express the electronic part in terms of numbers, and then I can use the fact, so I can re-express inside this the part that is really the hadronic part. So you see that actually you have the possibility to say it's the modulus square. So I can just rewrite it this way by saying that it's I can rewrite it in reverting the position of the initial and the final state for one of the two matrix elements. And then here I've got the dilepton momentum. And here I've got the momentum of the hadronic part. And this, now we're doing a summation over everything, all the possible intermediate states. So that's very good because actually we can think of using unitarity to express this as being the imaginary part of a correlator. And you see that, so the fact that we're doing the summation over all possible intermediate hadronic states means that in the end, by doing this trick, we don't have to get you to wonder or to worry about computing individual matrix elements here. We're just saying that it's related to the imaginary part of a correlator that does not involve anymore any specific hadronic stuff. You're back to something. Well, the only thing that is important is obviously you start from a hadronic state, which is given, which is the B meson, but you can imagine playing with what's going inside without specifying hadronic information. So that's a way of implementing quark-hadron duality, because now you can think of T as being just this kind of diagram where you have you start with a B meson that has a B quark inside with some given momentum that goes through a charm quark and then back to a B quark that goes into the B meson that you wanted to start from. And the imaginary part of this, so when I'm cutting this line, the imaginary part of this is going to, by unitarity, to give me the contributions I'm interested in when I'm computing the decay rate of B going to anything that has a charm. Okay, and so now you can think of evaluating T mu nu using the fact that you've got the large scale present, which is a 1 over, which is MB. And then by doing so, and I'm skipping because otherwise I will not have the time to finish, but I can come back to that later. You can actually write down, so do an expansion in 1 over MB of this correlator. So that means that actually what will happen is that you will say that what's going on here inside can be contracted. So you will start being with an expansion that will be just a point-like operator plus corrections. Because actually you're saying that here you're not playing the same game as before. Before we said we're taking the limit where MB and MC are very large both. Here we're going to use the fact that the charm quark is still not as massive as the big quark, and then when we're doing an expansion in terms of the big quark, then when we start the charm quark naively will have no time to propagate, so we can reduce its propagation to something which is just a point. And then when we do this and apply that to the decay rate, what we have in the end will be something like so these are just electroic corrections that can be computed. And then you have something that has this structure. I2R plus 1 over MB cubed plus corrections and so on. And so these Z and Y functions, they are functions of MC over MB. They can be, and there are series in alpha S. You can compute the corrections. So somehow we done once again a separation of scales. So these Z functions, they are short distance functions. And then you've got quantities that are matrix elements. So for instance, if you want to know what's mu p and mu j squared are, so I have to introduce some kind of funny covariant derivative that has a structure reminiscent of the discussion we had for the heavy quark effective theory. And so those matrix elements, they're telling you something about the residual movement or dynamics of your B quark inside your B meson. And so that's why you do have the fact that you cannot just, if you were to identify exactly the B to XCL new transition to the quark level transitions, you would have essentially just the beginning of this equation, this up to Z0R. But then, because you cannot do just this identification, you have a difference still between the B meson transition and the B quark transition. You do have information, non-perturbative information about how the B quark behaves inside the B meson. The one thing that you see here, which is also important, so you have several ingredients that are important. You've got VCB here, so that's what we're after. But you see that we have also MB to the 5th power. So obviously, defining properly what you mean by MB in this expansion is very important. And actually, the definition of a quark mass is obviously far from trivial. And so you could imagine, for instance, taking the MS bar scheme or a different scheme to define it. Actually, it turns out that given, so obviously numerically that will have a huge impact because it's the 5th power. And also, if you change the definition of the scheme you're choosing for MB, naturally that changes the repartition that you have between what's inside this MB to the 5th and what remains in the expansion, the rest of the expansion between the square brackets here. And so the convergence within the square bracket might be affected by the choice that you make for the scheme of MB. And so actually it turns out that, so this MB to the 5, so it's very important to determine carefully the value and the scheme of MB, and actually choices of scheme. Sorry. Choices of scheme. Choices of scheme impacts the convergence of the series, and actually you shouldn't use actually anything related to so-called short distance schemes. You should actually find schemes that will integrate inside the definition of the big quark mass a part of the long distance dynamics. And so you've got several schemes that allow you, obviously, that you can define precisely and determine the value, corresponding experimental value very precisely, but that are to choose over this kind of short distance scheme. The last element here that I wanted to add is that you need, in principle, you could, so how do you determine these matrix elements that remain in your expansion? So in principle, you can think of measuring moments of the lepton energy, for instance, and you can compute them in the same way, but so you will just do an integration here. So you will integrate d gamma multiplied by some power of the energy of the lepton. And so that means that afterwards, you will have to do an integration of the same expansion of T mu nu, but with a different weight. And that will give you an expression which will have the same, a similar structure as gamma, but with different values for the Z functions multiplying the unknown matrix elements. The problem is that experimentally not enough uncorrelated information can be extracted. From this. And then that means that actually you do have to do a combined analysis of B2X CNU and B2XS gamma, assuming the standard model again here. And that's a bit more tricky because we said that this kind of process is a flavor changing neutral current, so potentially more sensitive to new physics. Whereas B2XCLNU, in principle, you would tend to think that they're less sensitive to new physics. So it's a caveat that you have to keep in mind. If you do so, you can do a determination of all the matrix elements up to a reasonably high accuracy, which allows you to put back this information inside the expression for gamma and then extract out of that VCB. So extract this way mu j and so on. There are higher order matrix element condensates of interest, but to obtain finally VCB. So don't worry, Julia, I'm going to finish very briefly on VUB. I'm not going to be as extensive, and I should be on time. So VUB, you can in principle do the same thing for exclusive versus inclusive. So typically for exclusive, you would do B2 pi and nu. That's again a question of knowing well the F plus form factor. You do have again the same issues with lattice to extrapolate, so from low recoil to large recoil, and that's generally done once again using a Z expansion. You can actually imagine other processes, and that's actually something that is done. For instance, you can imagine looking at lambda b to proton mu nu. That's something that is done. You can imagine doing things like b to s k nu, and that's also done. But the main contributor to the discussion is b2 pi nu. I'm not going to spend much time here on this. For the inclusive, so I just want to say that it's a much more complicated business than B2XCLNU. So because in principle, you could do the same as for B2C. But the problem is just that it's very identifying a state with a final charm is reasonably easy. It's much more complicated to do that in an environment where you do have also the charm here. Just to give an idea, imagine that you're looking at B2X whatever. Then if you think in terms of the energy of the lepton, then you would have something like, I don't know, this for B2XCl nu. And because VUB is much lower than BCB, then you have a suppression for B2XU nu. That's related to the fact that BCB is much larger than VUB. So there is, most of the time, you will simply not be able to see very easily the B2XU and nu contribution underneath the B2XCl nu, because you want to do the summation of everything. So the only thing that you can do is actually to consider the place where you cannot access charm because you're in a region where simply kinematically you cannot produce a charm, and then to cut and just to consider the remaining region here for the analysis of B2XU and nu. The problem is that then when you're doing that, in principle, you can do that, but that means that you do that in the restricted kinematic range. And so all the discussion that we had before about summing over all configurations becomes very tricky because you're doing this cut. So you have to introduce new non-perturbative ingredients that are much more complicated than the previous one. So it's not matrix element, it's so-called shape functions, so which involve a lot of modeling. And so that's why the status for B2XU and nu is far from being satisfying at this stage. And so I will just show you to finish one plot because I showed too many. So if I'm just looking at this, yeah. So this is just an illustration of the current situation for VUB and VCB. So here you've got the various colored ranges correspond to the determination that are exclusive. So for instance, VUB, that will be B2 pi, VCB, that will be B2D, B2D star. There is also a common determination of VUB over VCB using lambda B decays. So you see that they agree more or less together. The problem comes from the fact that the cross correspond to inclusive determinations. And you see that here, the agreement is not so good. So that means that, well, you can toy with the reasons for that, but as I try to highlight here, there are quite a few assumptions coming into those various determinations, and probably a part of the reason for the discrepancy is related to the theoretical assumptions and the assessment of the uncertainties on this side. Okay, and so I will finish here to be on time. Next time I will go on with the rest of the tools that we have to obtain information on the CK matrix, because here, as I said before, I have focused on the moduli of the various CK matrix elements. And then we will see neutral mesomixing and also how to determine the phases of the CK matrix before putting everything together. Thank you very much for your attention.